Okay, welcome back, everybody. So one thing you'll learn if you haven't taken a class from me before, but I really enjoy reading the feedback you do on the little last question, the survey on the problems. I read that carefully. I listen. I try to make things better. I can't fix the room. I've been trying to fix the room. It doesn't seem like we're going to get a bigger room without a major disruption, like class is suddenly Monday at 9 a.m. That didn't seem very good. So we're probably going to stay in here. That was one thing people brought up that I don't have a great fix for. But some of the other things you said, I will try to adjust and accommodate. One thing a lot of people asked, like, what the heck is a context? Like, where is that even coming from? So now that you've thought about it for a little bit, if I had said this on day one, you wouldn't have listened, or it wouldn't have made sense. I think if I say it today, it'll just make sense, and then it's a very natural idea, actually, I think. So just a quick, before we get into the main idea, what is this context business? Okay. I said that we're going to use the language of differential equations, difference equations in class, right? So you're going to see a lot of models of systems, or you're going to use previously authored models of systems that start off looking a lot like your standard nonlinear difference equation, okay? But let me just write it out here. Okay, so when I write a math equation like this, I'll use this as my state vector. This is the input vector. This is a pretty standard notation for random disturbances that could be entering the system. If you want to model stochastic systems with just a deterministic f, then you bring them in through an input port. This is just the time. This could be any parameters, masses, lengths, stuff like this, fixed parameters that are not varying in time. Okay, so that might be like the slightly richer form of a difference equation that you might write to author a system, whether it's a perception system or a physics system or a controller, okay? And actually the state and the input, they can be pretty rich, right? You can actually have discrete states, continuous states. You can have multiple inputs, multiple ports. Okay, and for any given system, there's a lot of different questions you might want to ask about that system. When it's a multi-body system, you might want to ask, what's the center of mass of my robot right now? And that would potentially be a function of x and u and w and n and p. And all those things are different, for every system. The size of x, the type of x could be slightly different. Okay, so instead of asking an API where you pass in, n strange arguments every time, we just did the natural thing, okay? And we said there's this struct out in the world, okay? Sorry for the pseudocode here. Whoops, context, which has in it x, u, w, n, and p, okay? And so you just fill in that struct, and then you pass it in as a way to pass in all the arguments. Okay? That's all the context in. It's just one place to write down all the things. Some systems might have complicated x or u, if there's multiple input ports or whatever. Just think of it as the struct that you're going to pass into all the functions, so that it's kind of like your quargs or something in your dictionary, quargs in Python or something like that, but it's just trying to summarize all of that. Yeah? Great question. Yeah, so the context is the actual values. The system defines, knows the metadata about how big is x and stuff like this, and can check whether you've passed in a valid context. Yes? The context is always mutable. That's the other important point, is that the system tries to be immutable over the duration of a simulation. So you load that in, and it means it's going to be fixed. All the parameters of the system stay fixed. There's no values that are going to be changing in the class structure of the system, okay? This stuff changes on a per time step basis, okay? So it's a nice separation. That way, if you know the context, then you can always rewind to a different context and get deterministic playback. You can save the context to disk, load it again. You know, that's the thing you need to know. And in the case of a diagram, the particular instantiation of, you know, what the context looks like is that you just have a list of subsystem contexts. Right, some array of it, if you think of it in array language, okay? So that's the natural thing. Every little system knows how big its vector should be, how many input ports should it have, and then if you have a diagram, you just need a way to store the values of that at a higher level. Is that kind of clear? Yeah.
So you want to say the context room is well, so that doesn't get modified.
That is true. Procedurally, if you want to save it, every time you pass the context in, it's actually, so Python throws away constness, right? The C++ is actually very strict about whether methods are const or not. Some methods, many methods will not change your context actually, intentionally, but some of them could. So making a copy of your context is a safe way to store it away. Yes? Yeah, so I mean, you can do things like, if you want to take the gradient of the dynamics with respect to some elements, you can make this an autodiff variable, for instance, and pass that through. So a lot of the templating, for instance, in C++, it's templating, but if you want to pass different types through, that all happens at the level of the context. It supports, you know, more advanced operations like that. Replay, and even just sort of, I don't know, separation of church and state. I guess the system is sort of the mathematical model, and the context is the data, right? So it's even just conceptually, I like them being separate. Yeah.
What's like the most general definition?
The physics engine is a very general system. It exercises a lot of the pieces of the systems framework, but not all of them. Systems, they can be hybrid. They can be both discrete and continuous simultaneously. They can have events defined of like, so for a physics engine might define an event of when you come into contact, but a message arriving on a network protocol is a different type of event that some systems have. They can be multi-rate. They can all these complicated things they can define. Many of the ones we'll define in the class are simple discrete or continuous time systems. Most of the definition, the metadata of like what you expect in the context comes at the system level. So when you author the system, you're defining what are the parameters I expect. And then this is really just the data on the context. Cool, yeah, great. So, but I mean, that was a specific narrow question, but if it's like, you know, what's the meaning of life, or you know, could you write bigger, or you know, I like that you're stopping for questions, or I hate that you're stopping for questions, just give me the feedback. I really like the feedback, and I really do try to dial it in. A few other people said that the last lecture was kind of a, you know, I mentioned PID control very quickly, and if you hadn't seen that before, that was too quick, right? But please understand that the last lecture was kind of, you know, we're not talking that much about hardware. That was meant to be one lecture to kind of expose you to the things. You know, you should know that there's a lot of stuff going on underneath the hood, right? So it was more of an exposure. If you want, there's links if you want to read more. Today, we're transitioning into the first, I would say, core content of the class, where we're going through kinematics and the basic structure of the pick and place. I'm going to be going more slowly. I'm going to be stopping and asking you for examples and hoping that you understand all the bits, okay? So I tried to say that at the beginning of last time, but I hope it's clear that this is, you know, now we're getting into the equations that you really should make sure you try to understand completely. So let me tell you the sort of sketch. Yeah, please.
Can you elaborate a little bit more?
So the levels of, the question was, what the heck is this diagram and why is that useful, right? And I think we're going to see more and more examples, even today. But the dynamical systems that we will build are going to be very complicated. They're going to contain perception systems, planning systems, control systems, physics systems, rendering engines. The diagram abstraction is the way that you build hierarchies of more and more complicated systems by combining simple systems together. So it allows you to author. You could, have your rendering engine friend write an exquisite rendering engine without knowing anything about, mechanics or control. You encapsulate that in a system, and then you can compose them together and build really complicated systems. It's the way to build to the complexity that we're trying to address. Okay, so let me tell you kind of what we're going to do today at a view from 1,000 feet here, or 10,000 feet, and then we're going to go through it carefully. So, wait for my slide to load here. Here we go. Okay, super simple. We picked up our KUKA, our Shunk WSG. I used a little red brick last time. The goal today is to program sort of the complete stack to do the simplest manipulation possible, okay? You've got a red brick over here. You want to put it down over here. And I want you to understand the equations required and even a little bit of the code required to make that happen, all the steps to make that happen. With one major assumption, I'm going to assume that the perception is kind of oracular. That's what sometimes people will say, like it was given from an oracle, like the Oracle at Delphi or something, right? So oracular perception means someone told me the true position of the brick in the world. We'll do the perception from cameras in a follow-on lecture. Okay, so someone told me where the red brick was, but now I need to program the robot to go pick it up, set it down. Simple, okay? But we want to work through, I think working through that example will get you, will bring us through a lot of core topics. So a lot of that is going to be about kinematics. That's a focus for today. And kinematics is really, it's the study of geometry, which is going to be relevant for simple tasks like this, but also for perception tasks. If you're building NERFs in perception, that's a geometry problem. Okay, so it's going to be a lot of thinking about kinematics, and this is roughly how it's going to go. This is the recipe for picking up the brick. Okay, we're going to talk about kinematic frames. A lot of classes that talk about kinematics will write sine and cosine and things on the board. I'm going to try to not do that. The software can do that for you. I'm going to lift it up a level and talk about spatial algebra, basic algebra of how you compose frames and do operations on that. I think that's the right level where you can do a lot, understand a lot, and work with, the lower level equations we'll ask you to do once on the P set, but not mostly in the class. Okay, so we're going to talk about kinematic frames and spatial algebra. And then from that, we're going to just make a very simple sort of pretend the robot wasn't even there. Just think about the kinematics of the end effector, okay, of the gripper, and just imagine what I want my gripper to do in space and time. Okay, so that'll be the second step, is to just come up with my dream gripper motion. Okay, and then the third step is going to be to connect the joint angles, the commands I actually have to send to the robot, in order to try to execute as closely as possible my dream gripper trajectory. Okay, and we'll talk about how that is really just the spatial transforms that we will have already learned, applied recursively through the kinematic chain. Okay, and then the way we're going to convert our kinematic of the arm understanding into motions is we're going to write our first controller. We'll get halfway through this, okay? And I'll call it the pseudo-inverse controller, and today I'm going to just write inverse and tell you that you should be suspicious of that, but I'm going to write inverse for simplicity today, and then we'll study more what happens, whether that is invertible in general and cases like that. Okay, but that's going to use Jacobians and different velocities. So that's just the high-level recipe. When you're done, I hope you'll understand the basics of those pieces, and I hope the notes will complement if you have more questions. Yes.
Do you assume the trajectory of the
It'll be very explicit. You'll see exactly what we assume. I promise. Okay. So yeah, just to say it again. A lot of times when people are, the first lecture you might take in a robotics class about kinematics would start using a lot of trigonometry. Okay, and I'm mostly not going to do that. I'm going to try to talk at a slightly higher level, the sort of algebra level of kinematics, and you'll see exactly what I mean by that. I do have to start with just the definition, some basic definitions, of course. So let's just start with a point in 3D space. Everything I write today will be embedded in 3D, okay? 3 axes, just like the real world, okay? And I'll call it the point A, okay? I'm going to use P of A to denote, this is P for position, not for point. This is the position of A, okay? At some point, we're gonna have to think of this as 3 numbers, like an X, Y, Z position, okay? But even without that, it's just, abstractly, there is something that is a position, and I don't even have to write it down on the computer. I can operate on it as just a concept of the position. But you have to be a little careful. Position is only makes sense if it's in a coordinate frame, or if it's relative to something. Okay, so what I'm actually going to use is a slightly richer notation here, which is I'm going to put a B as a superscript on the left, which feels a little icky. But I promise when you start putting them together and the rules of composition, are going to work because the terms match. It'll be okay. It'll be justified then. Okay, so this is the position of A relative to B, right? So if I have B here, A here, okay, this is a vector, of A, telling me where A is relative to B. But if I need to now write that down in 3 numbers, I have to somehow choose the frame that I'm expressing, the coordinate frame that I'm expressing that in. Okay, so I'm going to use a subscript over here for the frame that I'm expressed in, which just tells me where, what does X mean, what does Y mean, what does Z mean. Okay. So somewhere here, I've got C. Too many colors, but it's important. This is my frame C, where I'm going to use X, Y, Z, okay? And you'll see that I'm going to always try to write in those colors, X, Y, and Z, and you'll see not only in Drake, and in most simulators, whenever you see a coordinate frame displayed, the X-axis is red, the Y-axis is green, the Z-axis is blue, and that's just like your signature. You can always, in anybody's renderer, you can sort of tell which direction things are going in. The way to remember that is sort of simple. X, Y, Z goes to R, D, B. Okay? Yeah, some people are like, I never realized. I've been looking at those colors the whole time, and I never realized it was that. Right? It's useful to know. Okay? So we might be doing a lot of this today. So we're always going to use the right-hand rule, and our frames are going to be so always right-hand rule X, Y, Z, and in general our world frame. So there's a few special frames. use W to denote the world frame. So we'll pick some canonical 0, 0, 0. We use to write everything in the world, okay? And because we're using this right-hand rule, we're going to put positive x. If I were to put my robot down in this coordinate frame, we'd call that vehicle coordinates, right? So forward would be sort of positive x. To the left is positive y, and up is z. That's sometimes called vehicle coordinates. As opposed to, for instance, airplane. Sometimes if you do Aeroastro, they'll go upside down. Everybody wants to still have right-hand rule, but some people like y positive to be right, which is sort of reasonable until z is suddenly pointing down. I don't like that at all. So we're going to go with vehicle coordinates. Okay. All right. So this is our slightly heavy but super useful notation with superscripts and subscripts. Okay. So this is this is the point of interest. This is what it's relative to or measured in, sometimes we say. And this is the expressed in, tells me what the coordinate system is. This one is only needed once I have to write it down in 3 numbers, on the computer, for instance. Okay, but conceptually, that is the quantity. This is just a representation of that quantity. And in general, all these rules are written up carefully in the notes, but if I were to write a frame up here, so I called this a point. I could write a frame up here. If I wrote a frame up here, then I would say it's the origin of the frame is what I'm taking the position of. So you can sort of, if someone says, like, what's the position of a frame, they're talking about the origin of that frame. Okay. So, good. In this case, this is just asking about what's the position of A relative to B expressed in C. I'm just saying if I said frame A, then that would be the position of the origin of frame A. Okay, so just a couple more things about that notation. It really it matters. Okay, so for years, I made a lot of robots work. I was in robotics for a while, and I wasn't super careful about my notation. And then I started collaborating with some people that are like religious about notation. And I thought, oh yeah, that's cute. I don't really need that stuff. And then I kind of, over the collaboration, I realized they get things right faster than me. And like they just make less bugs, and they less often have their fingers in the air, kind of going like this. Okay, the difference, especially if you're writing complicated, multi-body simulators, the difference of getting this right versus not is big. It really, I'm completely converted. I think it's worth a little bit of upfront cost being consistent in our notation. It will save you time later, because inevitably, and maybe some of you have done this, you'll write your basic, transform code or whatever, and then something was kind of upside down, so you're like, oh, maybe I'll flip the order of that, or maybe I was supposed to rotate this one first, and then that. If you haven't done it, you will do it sometime in your life, okay? Unless you just adopt this notation straight up, or a similar notation straight up. It really does make a difference. Okay, it is a little heavy to write all the time, so we have a couple of shorthands. So if I were to write PABB, then I would be okay summarizing that. Okay, so if we leave off the subscript, then that's just saying that the measured in frame is the same as the expressed in frame, because that's pretty common to do. And then the other one, if I were to just write PA, then that would be assuming that it was in the world frame. Okay? And then because we do a lot of this in code, we actually have a transcription of this too. So if you see it in code, you can't easily in your C++ or Python code write all the superscripts and subscripts, but you'll see us writing for this one. I'll do it over here. For this one in code, you'll see P underscore B A underscore C maps to this. Right? It works. It works. Okay. You'll hate it for a couple days, and then one day it'll save you, and then you'll be converted. Okay, so that's positions, which is a lot of what we need. The other obvious thing we need is rotations. Rotations are a little bit more involved. At the algebra level, though, they're not more involved. In the implementation details, they are significantly more involved. So we'll do, this is the rotation of frame A relative to frame B here. I'll write it more like I wrote up there, just to keep it consistent. Okay, and that mostly just works. Now, the choice of using a capital R, many of you will immediately associate that with a rotation matrix, and that is reasonable. You can actually go through the entire pipeline thinking about that like a rotation matrix, but I actually mean this one level abstracted from that. This is just a rotation represented however you like, and we will at times use different representations for rotation. So some of the ones that you'll see, we'll see rotation matrix, which would be a 3x3 orthonormal matrix. You'll see axis angle. You'll see unit quaternions. You'll see Euler angles, which we will always spell out as roll, pitch, yaw, because there are many Euler angles. This one I'm not going through all the details of right now. I just want you to know that there are many ways to represent a rotation on disk, and they have different names and different representations. We'll dig into those details when we need them later. Okay? But this is just, this could be used for any of those. This is the mathematical concept of a rotation. Okay? So let me ask a question then. So let's say I have two frames. I'm going to not write do the colors this time. I'll only do it when I need to do it to be clear here, I guess. But X, Y, Z. I've got another frame. X, Y, Z. So question, when does PBA in D equal PBA in C? Say it louder. Or what? So the proposal was aligned and on top of each other. Just aligned, right? So as long as the rotation between C and D is the identity, then the relative position of A and B is the same. Okay? That's just a quick, just exercise the notation and think about what it means to have the frames. I've got a couple others that may be useful here. So we're going to see them on the robot station. Okay, the gripper frame. It just depends on what the manufacturer chose as their canonical frame for the gripper, because that's what's in the robot description format. Okay, and then we have an object frame, which is our red brick. So given there's an object frame from some CAD model here, and there's a gripper frame here, now you have to think about your color coding. What are the possible values for P of O relative to G. And again, the G down here would then be implied, right? Yeah. Why do you say it must be B? Yes, the dominant term here, the way I think of it is the dominant term here is in positive Y, which looks like B to me, right? All right, just as getting the cobwebs out here, this is great. If I were to put a W there now, then the answer changes. What would it be then? Now the object relative to the gripper, which is this vector, right? But written in the world frame. Any other votes? You agree? Yeah. All right. So this is the level, okay, of roughly of that we're going to want to be able to think about things, is what these frames are. Now the math that gets you between those frames has a lot of sines and cosines. But the rules of composition are actually pretty simple, and they form an algebra. Okay? There's simple rules of composition. When can you add positions together and get another position that's in the same frame? When can you multiply? When can you take inverses? Okay, so that's what we'll do here, is we just need to define the same kind of ideas, same kind of quantities, but I want to define the rules of the composition. Any questions about that before I go? Yes. And the answer was, it was expressed in G. So the shorthand is, if there's nothing here, it means the same, you're expressed in the relative. Yeah, good. Do people like me going over there or staying in the middle? I know you probably want me to stay in the middle. Does it matter? Yeah. I'll try to stay in the middle, but if it gets really like, I want 4 boards, then I'll move over. Someone had a question back there? Yeah. I see. So I kind of painted the, yeah, you're right. I should have probably drawn explicitly W to make that more clear. Yeah. I guess I've just looked at this visualization so much. You're right. I should have put an explicit W there to make that clear. Good call. That's my bad. Okay. Here's the beginnings of our spatial algebra. And it really doesn't take much to develop. But having the rules in your back pocket is going to work well for you. Okay, so first we have the basic rule of addition, which is that positions can add. Okay? If I have this position and this position, right, then that is equivalent to this position, as long as they're in the same, they're expressed in the same frame. Okay, so now you can start seeing maybe why the superscript weirdness starts to pay off. Visually, as long as this matches this, then I'm allowed to, move things along. Okay. Because this is true, there's also an additive inverse. So P, A, B in F is negative B, A in F. You can subtract frames, or subtract positions too. So, but what if you get positions that are in different frames? Okay, the way that you change the expressed in frame is using a rotation, the rotation between the two frames. So multiplication by the rotation matrix we have P, A, B, G okay, so if I'm expressed in, I'll write that even a little lower to make sure that it's clear that that's a subscript rather. If I started in F and I want to express this in a different frame, then I multiply it by the rotation matrix that defines the transform from F to G. That's addressing the lower element. Now that's actually initially a little bit surprising. You would think if the frames can change not only in rotation but also in position, you'd think that it would need to understand the position difference, the difference of the origins between F and G also. But because of this thing that I've now erased, right, the fact that the only thing that matters of the relative position is the orientation, it's true that actually only the rotation matrix is needed to change the expressed in frame. Yes? You can take and put it here, so you can. So there are.
No, the other side of P, like on the other side, right.
That wouldn't compute. You'd need to do a transpose or something, right? This is a 3x1 vector. Yeah, yeah. So, well, sorry, no, okay. It is abstract, but still, I think even if you embed it, you can see why that would be a slightly strange quantity. Yeah, I do want to keep it in the abstract level, but you can of course take inverses of this rotation matrix, which we'll in fact I'll do that next. So I should say first that you can do multiplication of ARB times this times gives me the composition there, and then the additive inverse or the multiplicative inverse gives me, if I take the inverse of this, then I flipped B to A. Okay, and in practice, if it is a rotation matrix, the inverse is simple. It's just a transpose, and there's other things we'll get when we get into the numerical recipes. But this is kind of your basic beginnings of the spatial algebra. Yes? Yep. Yep. So the relative to this is just like the beginning and end of the vector. So I can only measure things, from A to B. Yeah. But I haven't said what numbers, should be used to represent that in any way. This is just a vector quantity that has a start and an end. Once I choose the numbers to represent it, then I need to say, where's my x-axis, where's my y-axis, where's my z-axis, right? And that's what the expressed in frame is here. But that's why, for instance, if I shift the expressed in frame, then this quantity could stay the same until this rotates. Right? They are meaningfully different ideas. Often, we use the shorthand because it is often the case that you might want to just take it and put the origin here and think about that vector in that frame. But there's many cases where you want to have them separate. Let me be more explicit about that. That's actually what I'm going to next. So what defines a frame, okay, has both a position, which is the origin, and a rotation, or an orientation, I guess I should say. So we're going to compose those two together into something that's called a pose. We'll call it X. B is the pose of B relative to A. So that pose includes both the position and the rotation that goes between them. Okay. Sometimes people will call them, we will sometimes call them spatial pose. Or, that's just because we're using it in the spatial algebra here. Okay, but this is the pose. The other word you'll hear is pose and transform are almost synonymous. Like in all practice, they're synonymous. You might hear rigid transform or spatial transform. Okay. I finally sort of realized, someone told me, that the way to think about this is that pose is a noun and transform is a verb. So they're allowed to, it's not like we're undecided. There's actually probably a right time to use the word pose and a right time to use the word transform, but they represent the same kind of idea, which is a combination of a position and an orientation. Yeah?
What's the difference between that and the
Conceptually, this has to have inside it the position of A relative to B expressed in some thing and the rotation. This quantity has both. Yeah, it's the combination of those two. And this is actually the workhorse for us. So if you get into the representations, this would typically be, you might think 4x4 matrices. That's pretty true, but it's actually 3x4 matrices are sufficient for rigid transforms. Okay, and we pass these around, and it's really good on GPUs and all that good stuff. Okay, so there's an algebra on top of the transforms too. Yes. A frame has a current pose, right? Just like a point has a position. I think that's an answer by analogy or something. Yeah. Yes, I would. That's actually exactly why it's not arbitrary that we've chosen multiplication for rotation matrices and addition for here. We want to imply the standard rules of addition and of the algebra. Yeah. Yes. It is the second thing you said. So let me say it. So because it's multiplication, if I have a point that's in C, then I'm gonna right multiply this thing by some point to take me from C to A. Then I could also do that. I think you should think about it going this way, because multiplications are going to be on the right. If I take a point on the right, then I'm first going to apply this multiplication and then this multiplication. This is one of the places where people be like, oh crap, and they start switching it, right? Because it is tempting to rotate in the other direction, but matrix multiplication operates in that way. Good, so this is, we do have the rules of the spatial algebra for the transforms too. They basically are exactly what you expect, and rather than just write it, I'll just say that right in the notes you see, I tried to make kind of a concise summary of the additive inverse, the multiplication, multiplicative inverse, right? The transform can be applied directly. It's okay for me to write x a b times some position, right? As long as my position's in the proper frame, right? So if I b c like this, okay, then it can do these operations, and they're all defined carefully here. There's an inverse of the transform. Okay, so that's our algebra. And then conceptually, if we want to do more complicated things with our robot, then what we're doing is just applying addition and multiplication of these basic quantities in order to program the robot. Yeah? Yes? You would think that, but actually it's never needed. So, yeah, you would think that, but it turns out that it's cleaner and never needed to have this. You can always have the implied frame there for everything you want to do with transforms. Let me think if there's a satisfying way to. I also, when I first started doing this, I said, oh, we're going to put an expressed in frame down here or whatever. But actually, yeah, it's just explicitly just never needed. I should be, I guess, the measured in frame, yeah. Good question. That's a very good question. Okay, so now that we're lifted up from points and positions and orientations to the level of these transforms and poses, now we're going to program our gripper. We're going to come up with our ideal set of transforms that are going to move our gripper around, okay? So I'm going to define some canonical frames. I've got my gripper here. I want a snapshot. I say, here's the object in space. I want to find some initial grasping frame that is a pose of the gripper in, let's say, the world coordinates. And then I want to maybe pick one that's a little bit above there so I can cut it back away nicely. Then I'll pick my next one that's sort of halfway to my goal, not running into the bins, and then I'll set it back down. And I just want to, the next step is to come up with a list of these transforms that are going to define the motion, the desired motion of their keyframes and the desired motion of the object. All right, so let's say that what we're given from the perception system is, as our initial sort of input to the algorithm, I'll call this the object frame. And I'll even say the frame is the object's initial position. And I might be given that in terms of, from a perception system, I might be given that, let's say, in the world frame. The position of the object in the world frame. Okay? And maybe I'm also given an initial gripper frame, say. And maybe I have a goal frame that's also given in some sort of a world coordinates. And that would be a pretty coarse thing. That would just say, like, the object's there, then it's there, and my gripper's currently here, so I need to fill in the details and say, okay, now I need an intermediate representation, which is the gripper, where the gripper should be in order to grasp the object, where the gripper should be where to place the object. So I need to define a few more frames, but I'll use my spatial algebra to do that. Okay. So we'll go in and we'll define, I called them the grasp, or the gripper location during pick. Okay. And then because, like I said, it's a kind of nice to not go directly to the position. It's a standard sort of approach would be to take a pre-grasp, so pre-pick. So I'm going to I'll pick a place just above the object, and then I'll go straight down into the object. That way it just simplifies the motion planning. I don't have to worry about my fingers colliding when they're coming in. Okay, so I'll make a G pre-pick. And then I'll back off to the same thing too. Something I'll call it post-pick. Okay, G place. I also want pre-place, post-place. Okay, and if I could just enumerate those, let me actually show you how that kind of works. I've got some code here where we'll step through a little bit that just assembles a list of these different frames. And then I can draw the gripper in a bunch of those different frames. So this is just my starting frame, my gripping, my pick frame, my pre-pick and post-pick frame, okay? And then this is my desired object position, pre-place, post-place, or place, pre-place, and post-place. Yeah? Okay, good. So just to show you what that kind of looks like, so of course we're going to make this into a trajectory with timing in it soon. That'll just sort of define my desired motion. Let's think about how we actually build up those different frames and their pose over time using our spatial algebra. So if we're given XO initial, XG in the world frame initial, and we need a few more things to start connecting the dots and defining our intermediate frames. We have to decide where we want the object to be relative to the hand. That's kind of our intermediate quantity. So I know my object frame is here, but I want to come up with what should I be my sort of happy place for where the object is relative to the hand when I'm doing the manipulation. Okay. Now you can imagine if I can decide this, which I will decide, it turns out that because the y-axis, is kind of along the fingers, it turns out that representing this as something like 12 centimeters into the fingers in the coordinate system, that's kind of a happy place for the center of mass of the brick. Okay. In the gripper frame, just like we have up there. And then the rotation matrix, that's pretty good. Now I'm assuming, I'm not taking into account the fact that the brick is symmetric. I'm just picking a canonical frame just to keep it simpler, okay? But I can make this with a few choices of a few rotations. If you think about this same picture I've got on the screen here, but if I want the gripper to be coming down on top of that red object, then I've got a gripper frame with the green pointing straight down. The object frame by default has got Y like this. So I have to apply 2 rotations, it turns out, to rotate the object into the gripper frame, into a comfortable position in the gripper frame. But I'm just going to decide that. I'm going to say, when I'm, a successful grasp has the orientation, or the position and rotation of the object relative to the gripper being this given quantity. And then I can use my spatial algebra to compose these things together and say, well, I knew the initial object. I know what the gripper is. I can make the gripper at the different positions. Right? So it looks kind of like this. So I made it 11 centimeters. I guess that was better. Must have knocked my fingers shorter on running into an object or something. I chose 2 rotations to make the object frame relative to the grasp. And then that gives me this rigid transform X grasp, X of the object relative to the grasp. Okay? And you can do multiplication and all the things you'd want in code the same way we've written for the algebra. Okay, and then I can use the multiplicative inverse to figure out what the grasp should be relative to the object. Okay, and then I'm also defining the pre-grasp as being directly up from the grasp. Unfortunately, in the grasp, frame up is going to be negative y. You have to remember your frames always. And then you can just start going through and defining these different quantities. So I want the gripper at the pick position to be based on the object at the initial position, chained with the object relative to the grasp. And I made the right, I took an inverse up here because this is the quantity I needed down here in order to make those chains work. And this, again, the notation saves you. Like you will get those backwards or wrong if you don't use the notation somewhat carefully. Okay. And then this is kind of a little window into why different representations of orientation are useful in different places. If I know I have an orientation here that's picking up the object, and another one here that's picking up the object, and I want to pick something that's kind of halfway through, maybe halfway in position, but also halfway in orientation, that'd be kind of an awkward thing to write in rotation matrices. It'd be kind of an awkward thing to write in quaternions or something, but it's very natural to write that in axis angle. And you'll see what's natural to write as you start to use them. I'm not trying to teach that now, just to say that there really are different times when the different rotation representations are useful. And so we just try to make it very easy to go back and forth. You can always go back and forth between axis angle and rotations and stuff. So I'll just pick I'll pick an intermediate point that's kind of halfway in position and halfway in rotation between the two. Yes? Yep. 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 There's a lot of good answers to that. So the question would be like, yeah, so I assumed a lot about the object, not only that someone told me where it was, but that I had its canonical frame and I knew like where that frame was relative to the object. Yeah, we're going to build versions of this that don't make that strong assumption. You can do things like look for nice flat faces on the object and put your finger nicely aligned with the flats of the object. That's actually a pretty good heuristic. And if you find some that have the flats of the objects are opposite normals, antipodal, then that turns out to be a super useful heuristic. So we can do things that are more still about the geometry, but less baked in the object knowledge. Yes?
Yeah, just a quick question about
yes? That is actually rotation matrix call. That it's just, I could have done it many ways. That's actually, I could have written that as roll, pitch, yaw, too. But I just think because people often confuse which order they go in, I thought it was a little bit more clear in the example to use spell out, make X rotation, make Z rotation. But I think going forward, I would just say you get used to roll, pitch, yaw, and you just call that a roll and a yaw. Yep, good. Okay, so the first time I typed this in, I forgot about like the clearance stuff, and I don't know, I thought it was funny, so I put it in my slide. Yeah, I typed this in, and I had my beautiful trajectory, initial and final, and then we simulate it, right? So we're not just imagining this. At some point, we're going to simulate it, and I just ran smack into the bin, and the fingers broke, and the robot got kind of increasingly unhappy, and then eventually snapped itself loose. So, that intermediate, you actually have to add some clearance for the intermediate, in order to get that right. Sorry, that was just amusing myself, mostly. Working on robots is great for like making yourself laugh in the middle of the night. You write a walking controller and suddenly your robot's walking backwards. Like what the? And it's typically because you didn't use multi-body notation. Okay, so we have a sketch now. We have these like key frames of different orientations and positions of the gripper. Now we have to specify the timing. So we have to somehow roll those out over time and embed them in time. Tell me how long it should take to go from one to the other. Yeah. So that we're gonna have to address that. So I know that's the last piece of today's lecture, is going from this end effector control into joint positions. Yes. Oh, okay. Yes, so we're going to be careful about wind up and other things like that. But that is a bit like what you saw when I started running into the bin, and it just started pulling harder and harder and harder, and then it just finally went like this. But this was because this was the simplest controller, and we're going to build much better controllers that don't have that problem. Yeah, but good call. That you have to be thoughtful about that when we get to it. Okay, so the simplest idea of just we could just specify at what time. In fact, in the code even, I do specify at the bottom. I specify all of the frames for the gripper, but then I also set the timing. I say the initial time is 0, the pre-pick time is something. I try to scale it based on the distance it has to travel, but it's pretty simple. It's basically 10. 10 seconds I want to be there. I'm going to add 2 seconds to go from the pre-pick to the pick start. Just kind of spell out the timings like that. And this is, by the way, extremely conservative timings. I'm not going to make any money in the restaurant industry if I'm moving that slow. Okay, but just to get things. It's partly because my controller is simple in this particular example too. Okay, so you spell out the timings. Now the question is, how do you take those from those keyframes that are in position, orientation, and time and connect them together? And there's lots of different ways to do it. Positions with their additive properties can be interpolated very naturally. You just take a linear interpolation in position, and that's pretty darn good. Rotations have to require a little bit more thought. You can't just take 2 rotation matrices, for instance, and just draw a straight line through them and get a rotation matrix. Let me even say that somewhat carefully. So let's say I have rotation of the gripper pre-pick in the world, and I want to go to rotation of the gripper gripper pick in the world, right? Let's pretend that this is in 2 by 2. I'll do an example of 2 by 2 matrix, rotation matrix. But we could ask this question of how do you do the interpolation in any of the rotation representations. But I think it's simple like this. So a rotation matrix in 2 by 2, you might remember what those things look like if I wanted to just rotate around by theta in 2D. It's just a single rotations. Okay, so if I wanted to rotate, let's say, from theta equals 0, which would be, so theta equals, I don't know, pi over 2, that would be 0, negative 1, 1, 0. Okay, but theta equals pi over 4 is absolutely does not equal the average of those two, right? Does that make sense? It's because it lives on, in this case, the unit circle, okay? And in the 3-dimensional rotations case, it lives on the on SO3, okay? The special orthogonal group in 3 dimensions. So you have to live on this sort of manifold of reasonable rotation matrices. Many ways to think about that, but rotation matrices have to be orthonormal for instance. And if you just average two orthonormal matrices, you don't get a new orthonormal matrix. So there's a simple recipe. There's an equivalent of linear interpolation between positions that you can do for rotations. It's called SLIRP, spherical linear interpolation, SLIRP, okay? So it's something like spherical linear interpolation. Interpolation. Okay, so but there's a way to sort of smoothly go through, let's say, the rotation matrices or with a linear interpolation. So we can put that all together. In software, the time specification is embedded in a trajectory, okay? So we have many different trajectory classes in Drake. You might have heard of Bezier curves or B-spline trajectories or piecewise polynomial trajectories, okay? But one of them we've got hiding in here is quaternion SLIRP, okay? Which allows you to define snapshots of rotations using a unit quaternion representation and beautifully interpolate between them. And it's piecewise because it'll interpolate between each snapshot, okay? And you can combine that with piecewise polynomial, which would be like the linear interpolation of the translation. And the composition of those two is piecewise pose, which would do the linear interpolation of the positions and the SLIRP for the rotation. Is that clear? And that's what I've been rendering this whole time, is the nice interpolation of that. Yes? So in the code, you can see I make the gripper frames like this. I visualize the gripper frames. You then just call, like for the pose trajectory here, you can just say make the linear pose. I give it all the different poses and it will combine them. But I made the choice. It's not a default in the sense that I made the choice of calling piecewise pose constructor in order to get a piecewise pose output. If I had called piecewise polynomial, I would have gotten something different. Yeah. You also have to just decide when you're going to open and close the trajectory, the gripper. That's the last piece. But that's similarly a simple trajectory that says I'm going to be closed with the object and then opened. In this case, it turns out that that particular gripper, you can just tell it to close all the way, and it's got a force limit. And so you don't have to worry about the width of the object, for instance. You can just say close, and it'll stop nicely, maybe squeeze a little hard. Don't do it to an egg, but it mostly just works. Okay. That much of the recipe, sort of good. Let's just take a second to appreciate what we did and didn't do in that, okay? So the mechanics of moving frames around is, I think, pretty natural and pretty good. It's natural, I think, to think about the position of the gripper as you do things. But making a plan only in the gripper does ignore some things, right? It doesn't think about, for instance, if your elbow might have to bump into the table in order to get there. Or even you could accidentally ask for a gripper position that the robot can't even reach, right? Or you could ask it to move at a speed that the joints aren't capable of producing, right? There's all these sort of constraints that come from the joint representation that are not expressed in this end effector gripper view of the world. Okay, but if you take your sweet time picking up objects, then it's just completely good. Okay, yeah, so what I thought you were asking before was the next piece of the puzzle, which is that if we go from, we have now an end effector position, but at some point we have to come up with a position trajectory for the robot, right? The hardware station. Its input is not end effector position. Its input is Iwa position. These are the joint angles. So somehow we have to map from our target end effector position, to back to commands in the joint space. And that's the job of forward kinematics or inverse kinematics of the manipulator. Okay, so Q is my joint positions, right? This is even maybe I'd call it Q desired in the previous lecture. And I'm going to understand the mapping from Q to the end effectors. And similarly, I want to be able to invert that, go from a desired end effector to Q. So how do we bridge that gap? Okay, so the first thing to realize is that when you load from these robot description files, I told you before, there's link. Link tells you what the objects are. If you scroll down enough, you'll also see there's joints defined. Those, the EWA has just 7 revolute joints. Okay, so revolute joints are just transforms that are dependent on the joint angle that tells you how do you go from one link to the next link's coordinate frame. Okay, so that picture I've been showing you here has coordinate frames drawn, RGB, through all of the different links. Okay, each one of them, between them, is a transform that depends on the joint in a simple way. We'll show you in a second. Okay, and the work of going from this frame back to this frame, or vice versa, is just a composition of the spatial algebras through the joint-dependent transforms. So if we understand how to go across one joint, then we understand how to go all the way across the tree by just the composition rules. Okay? And the standard way that you go through the joints, or to define one joint here, is, you'll see these sort of standard pictures of robot joint definitions. Okay, so I'll have, let's say, link 1. I'll have link 2. And I'll have a joint here, okay? So, well, I should actually be careful with my colors here. So I'll have a body frame in this. Maybe I'll call this body 1. I'll have a body frame over here, body 2. We can make the joint frame here expressed in body 1, okay? And we can make the joint frame here expressed in body 2. And then we can say a revolute joint, a pin joint, is just a pure rotation around these frames that tells me the relative rotation of this frame relative to this frame. And that's the only thing that depends on Q, on the joint angles. Did I say that well enough? So it might be if I called this, let me see, the composition from body 1. Sometimes this is called M, and this one is called F. Depends which notes you're looking at, okay, but let's just say M and F. And then I have the transform from M to F, depends on the joint angle, Q. But then I have another fixed one that goes from F to body 2. And so I can understand, as a function of Q, what body 2 is relative to body 1 just by the rules of composition. Okay, so it's kind of actually interesting. So a lot of people think that every time you add a joint to the URDF or the robot description file, that you're adding a degree of freedom to the system, right? But it's actually it's actually different than that, right? So by default, if you just add bodies to the system, they all have 6 degrees of freedom each. They're all possibly free to rotate in any position or orientation. So when I add a link joint, when I add a revolute joint, you should actually think about that as I'm actually taking away 5 degrees of freedom and turning that into a 1 degree of freedom joint. Okay, and I'm specifying that those frames must be related by this equation, which depends only on that one thing. Okay, so then the rules of composition just go right through. Yes?
Is there a standardized equation for those arguments that you specify? That would different arguments.
Yes, so the robot description format has specifications for how you would say a revolute joint, how you would say a prismatic joint, how you'd say a planar joint, and then those equations are all coded once as, as a dependent, the exact formula that implements this as a function of Q is different depending on what the joint type is. Yes? This is Tommy's favorite question. I almost want him to answer, but so the simple answer is yes. If you have 6 degrees of freedom, then you can actually find a solution for the joint angles that match. 7 gives you 1 extra degrees of freedom, and it's the standard 7 degree of freedom arm. Of course, there are limitations, and there are actually multiple solutions in cases, and so you have to make choices. And you should ask Tommy, because he... Oh, you want 7. So 6 is a bad place to be, because then you, as soon as you reach into a kitchen sink, you will wish you had 8. Because you're trying to stick your robot's elbow down into the sink because you've got a big arm sticking off the back. So the value of having those extra links is in what you can do in the workspace is very apparent once you start working around. So as soon as you have, so maybe the math way to answer that would be, as soon as you have other constraints like obstacles or something like this, then the limitations of having the 6 subject to those constraints will become apparent. So you want the extra degrees of freedom. Yep, just because I think so the complexity increases, the cost increases, the weight increases, but I think some robots do have more, Yeah. Oh, go ahead, Tommy.
I was also just going to say that the human arm, if you think about it, has 7 degrees of freedom. So to some extent, anything that you can do, modulo moving sort of in a shoulder relative to your body, you should be able to do with a 7 degree of freedom robot arm.
Yeah, I mean, we can do pretty complicated, I'm rotating at my elbow, right? People say that. Actually, yeah, I think he's right. That is the inspiration. I think he's right about that. Yeah, but we're squishy. And that can be useful at times. I'm squishy. I shouldn't say anything about you guys. Okay. Good. Yeah. So for instance, the hand is the kinematic tree of the hand uses the same exact math, but it's a slightly more interesting kinematic tree, right? So I can plot the world body, and it's in a world frame, okay? But then I have the hand root, which this is a floating hand. That's why it's not attached so far, okay? But then, I've defined my kinematic tree where each one of those is revolute joints going up. And if I want to compute the kinematics, the locations of all my fingertips, it's just a matter of recursively solving those transforms up and down the tree, right? And if I have an object, my foam brick in the scene too, then that's got its own 6 degrees of freedom. It's got its own free pose by default. All right, so actually, quick quiz then. So how big is the configuration vector Q for this example? How many, if I were to say plant.getPositions, context, yes? Yep. Yep. Good. Yep. But we also have the degrees of freedom of a foam brick, and this hand is actually not bolted to the ground. It's free to float right there. So that actually gets to be, so okay, then this question. So if I want to represent my floating brick, how many Q elements do I need to represent that? That's what everybody would say, but that's not actually right. Because, well, you could represent it that, but you'd have a singularity in the transform. So it turns out you actually need 7 numbers to represent position, or you need 4 numbers to represent 3D orientation without singularities. So this actually has a unit quaternion plus the 3 positions. And this one similarly has a unit quaternion plus the 3 positions. So the whole thing comes out to 30 degrees of freedom. Yes? Yep. I can start there next time. Yeah? Good. Okay, we'll finish it up next time. See you then.